Good morning, everyone. This is Jim Chastain with EasyPower. Happy Cinco de Mayo. Today, our refresher episode is on device coordination. And so I welcome you to Thursday morning. So we've created a multi-part series on this subject. This is actually the topic of the better part of a day class during a regional training session. And by dividing it into smaller chunks and spreading it over a couple, 3 weeks, it gives us the ability to get into more detail and hopefully allow the audience to assimilate and maybe practice some of the information as we go along. Today we're going to be focusing on the toolbar and the controls and a little bit about what the display, or how to get the display on the screen. And then in the future sessions, we will be going into more detail on the principles of coordination and how to utilize the tools on various systems of different sizes and the pros and cons of some of the options involved in the EasyPower tools. And again, the audio from the audience is muted, so if you have questions, please either send them on the chat line or enter a question on the question bar, and we will get to them at the end of the session. Appreciate the feedback. Okay, so coordination in electrical power engineering is actually a specific branch that deals with the protection of electrical power systems from faults through the isolation of the faulted parts from the rest of the system. So the goal is to keep as much of the system online while isolating the fault and preventing any additional damage due to the initial incident or fault. In EasyPower, the module that we utilize to simulate and analyze this is called PowerProtector, and it provides the tools to complete the analysis and visually simulate the protection scheme. Before these types of tools were available, engineers had to take performance curves or TCC curves in either onion skin or mylar and overlay them to see how they would react or how they would basically trip based upon the short circuit calculations of the circuit, and then come up with other techniques of making adjustments to make sure that you had some sort of coordination between series protective devices. So as we launch the tool, you'll see that in the EasyPower desktop, there's at the top of the screen a focus banner, and the coordination, the PowerProtector module, is indicated by these two little curves, which are supposed to represent a graph, and the label is coordination. And one of the things that's good advice for anyone, but in particular first-time users, is you want to start with a relatively simple circuit at first. If you have not done device coordination, or better still, if you've not done short circuit or arc flash analysis, you're better off with the tools going through a very simplified example that brings you to a point that's, if you will, one essential connection between your utility and a basic load that you need to have analyzed before you input data on the whole system. I'll show a little bit about what this means in just a second. Once you've got a clean one line, then the tool allows you to change focus to coordination. So I'm going to go to the tool here and show you what I'm talking about. So this is the focus banner at the top, and I've got a one-line diagram that kind of represents a typical addition to a system or a feeder distribution system. And because I've created the one line in Database Editor, the next step is to go to short circuit or to coordination. The tool will not allow me to change focus until there's a requisite amount of data, at least for that particular type of analysis. So in the case of short circuit, it's saying, okay, it can't enter short circuit with incomplete data. It'll give me a report. So in this case, I want to say yes, and I can see that I have an MCC, a motor, and a cable that don't have complete data. Another note for beginners, when you are in a display of a specific window, all the windows that have been created are stacked up here under the little Windows icon, and what I'm looking at is the one that's checked and on top. There are two ways to get out of this. One, I can just choose the window that I want to go to, or I can go to the little E icon at the top and close. So that closes the top report, and consequently that particular report is no longer in the list. Okay, back to where we were. To be able to go to, so the recommendation that I make is, rather than draw a complete system and then start trying to figure out why you have problems with it, I would recommend essentially minimizing the complexity of the system. One way to do that is either not draw the whole thing, or if I have drawn it, deactivate portions of it until I'm down to the point. And so in this case, I want to deactivate this MCC panel and its breaker, and then deactivate this panel and its breaker. So now what I have is a one-line diagram that goes from my utility through a relay, through a switched fuse, transformer, down to a load that I know at some point in time I'm going to want to be able to coordinate through this whole chain. The reason for isolating it and making it simplified is that now that I can actually go into short circuit focus or coordination, independent of whatever problems I have out here, I can go through the analysis and see why the data is important, and as I go back and look at what's missing in these other elements, I will understand either my data collection was inadequate or my data entry was inadequate. So that's just a word to the wise. I guess in beginner's case, start small, start with a very simplified diagram, understand the principles that I'm trying to apply during the analysis, and then expand it out as I get the results that I expect to see. So we'll kind of get into more of that as we go along. It's surprising to me how often we will have a file sent in where there won't be any results at all, and the engineer has drawn a complete one-line diagram and can't understand why he's not getting any results, and it's because he usually hasn't characterized his protective devices. Okay, so now as we go to coordination focus, we see the banner change, and there's a number of icons now available to us in terms of what's required for coordination. And the interesting thing here is it includes the short circuit, most of the short circuit capabilities, and the coordination icons as well. In terms of short circuit, what it allows us to do is to look at individual branch currents, both at half cycle, 5 cycle, and 30 cycle time snapshots, and to look at various faults in addition to the arc flash calculations. Okay, so one more point on that. Part and parcel of completing a coordination study is not just coordinating the protective devices, but also mitigating as much as possible the arc flash incident energy calculation. So one of the neat features of the tool, and we'll get into this more so in some of the follow-on sessions, is the fact as we make adjustments to the protective devices, we can see real time what that impact is on the incident energy and understand whether that's the direction we want to take that particular protective device. Okay, so what we're going to do now is look at the device curves. One of the key elements and features of coordination module is the ability to look at each of these protective devices and And it's relatively important to make sure, as we're looking at a one-line diagram, that we can distinguish between the loads, the elements that need protection, and then the devices that are going to do the protecting. So let's kind of get in and talk about that. So what I've set up here is an example of kind of a hodgepodge of different devices, and we're going to go into the coordination focus and then look at each one of these devices and see what the curve should look like. So here's a Class J 100 amp fuse. If I just highlight it and plot the TCC curve, before I go there, let me talk more about the bus bar, or the focus banner. So we're in coordination focus. Obviously, we can zoom and control the window. We're going to get into the options next week, but what I was indicating earlier is on the one-line display, we can short the buses, look at the branch current, and these are all features that are usually handled in short circuit analysis. So right now we're showing if this bus were to fault, we would see a total of 20,390 amps coming from the utility into this bus. And that's by virtue of the fact we've picked out half cycle time point, three-phase fault, and we faulted the bus. We can also look at the current that would be there at 5 cycles and then at 30 cycles. Again, these are all features that are available in short circuit. Likewise, we can look at the types of vector current. So phasors, if we click on the plus sign, this gives us the positive phasor current, the negative, and the zero sequence. And as long as they're in balance mode, all we should see is the positive sequence results. If we go to line to ground, it's saying that we're assuming the A phase is faulted, so we're going to change our one line to display A, which is okay. And now we're looking at the half cycle A phase current. If I look at the positive sequence, negative sequence, and zero sequence, you can see these are all effectively the same in terms of the current that's going to each leg of each phasor. And then likewise, if we go to a line to ground fault, here we're faulting B to C. So if we looked at the branches, we'd see B and C current. Or if we looked at phasors, we'd see positive sequence, negative sequence, and zero sequence would all be different values. More on that as we get into the analysis of the different faults and the coordination of same. At any rate, all these controls are there, and they will come into play as we entertain different coordination targets, I guess. So we're doing a three-phase balanced fault. I'm going to plot what the TCC curve for a Class J 100 amp fuse looks like. For those of you that are not familiar with the TCC format, what we have here is current on the horizontal axis and time on the vertical axis. So this is a time current curve, and it's log scale. So as we start at 0.01 seconds and go to 0.1 seconds, 1, 10, and 100 seconds, the current, in this particular case, the fuse will be able to withstand less and less current as it goes for a longer point in time. As I position the cursor over the curve, I can see down on this bar at the very bottom of the screen what the value is of that curve on the display. So if I put my crosshairs right there, I see at 654 amps, this fuse will blow or clear in 96 milliseconds. All right, so that's pretty much characteristic of a Class J fuse. We're not going to save changes. We want to go look at this fuse and plot it. Again, higher current, a little bit of a different shape. It's been engineered to basically withstand current at a different rate. And the reason there's thickness is that there's a minimum clearance, a minimum, if you will, point where it starts to melt, and then a maximum point or that we guarantee it to clear. So at, in this case, 4,000 amps, it'll start to melt at 71 milliseconds, and it's guaranteed to melt, so we get back to 4,000, to have cleared in about 115 milliseconds. All right, right now we're just looking for how the shapes of these curves look. A motor, I can highlight a motor and look at what's produced there. So this is the starting current for this motor, and what it tells us is when full voltage is applied to the motor at 0.01 seconds, it will draw, or can draw, as much as 135 amps and gradually decline to 0.1 second to somewhere near 82 amps, and it could stay as high as 82 amps for another 3 or 4 seconds, at which time it, in normal operation, it would drop to something less than 15 amps. So normal operation for the motor current versus time is out in this area over here. If the current were to spike and to fall at a higher value, then we would expect to have to protect the motor or protect the rest of the system from a fault. As I double click on the element itself, I can go in and make temporary adjustments to these settings that draw these curves. So in this particular case, I want to also plot the thermal limit curve, and as I do this, it's going to indicate the stall time and the potential for damage based upon a certain level of current. As I apply this, you can see that my thermal damage curve is plotted, and this means if the current gets to this point for this amount of time, we could potentially see thermal damage of the motor itself. So for coordination purposes, we have to walk kind of a fine line where we need to stay to the right of the motor starting current, but to the left of the time and current indicated by the thermal damage curve. That's the case with most motors. All right, let's look at, so this is a breaker, electromagnetic breaker, and if I highlight it, all right, still got it, and plot it. You can see that, well, I actually have two breakers here. One is a thermomagnetic and the other is solid state. Thermomagnetic is controlled, or at least the plot points, is controlled by the set points, and there's virtually no variability as far as making adjustments. And this curve is my solid state curve, and this is my thermomagnetic breaker. Where there's a need to make adjustments in the thermomagnetic, it's done with the size of the breaker or the selection as far as trip amps. So now as I change this to a 30 amp breaker and apply, you can see the curve shifts on the display. If I go back to, and so if this is going to be an upstream breaker, then I want to set it at 110 amps so that it will trip after this previous breaker, then I'd need to make a different selection on the phase trip. We'll talk more about curves, breakers as we get into the curves. Likewise, so now I'm opening up these curves either two ways. I can double click on the one-line diagram, or I can double click on the display of the curve in the TCC display. So as I open up the solid state breaker, I can see under my specifications I selected a molded case, but it has the ability to have a solid state trip, and so these are the dial settings on, and this frankly I'm not even sure if this is an existing definition of a part, but we're able to make these adjustments, and as I change these particular settings, which are done under the phase trip setting, you will see that the display curve changes slightly, and consequently I can make changes by changing the adjustment and thereby change the shape of the curve. I can also do the same thing with the adjustable settings by left-clicking on the curve and dragging it, and you see in the dialog box that it shows me what the resulting dial settings will be, and as I start to overlay loads and transformers and other elements that I want to protect, that's exactly how I will perform coordination, is I will make adjustments on the display and then visually see whether or not I'm effective in protecting or limiting curves to certain elements. Let me look at a couple more. Okay, another protective device that's in the system very often, and usually it's for protecting transformers and more exotic trip settings, are relays. And so in this case I've enclosed a transformer and a relay and the resulting trip breaker that's going to be controlled by the relay. And what I'm looking at here in my TCC display are a couple things. So you see here we have an inset for a one-line diagram, and we have the logo and time current label down at the bottom, a legend. I can take these, put these on or off the display by these little check boxes at the top, and sometimes it gives me better visibility of the display. These dotted lines and these straight lines here on the right are the transformer damage curves, and these are basically indications of how the construction of this particular transformer requires protection. And again, these are plotted, if I double click on the curve, by the data dialog box that we entered when we defined what the construction of the transformer is. In the case of the TCC, most transformers by default plot both the withstand curve and the unbalanced derating and the frequently fault curve, all of which can be modified or changed if we need to look at what options we have in deciding what our coordination scheme needs to be or what our options are in terms of where we're going to mitigate energy or protect the transformer. This curve with the curved upper section and straight lower section is the relay. This little dot down here is the inrush current for the transformer, and what it says is that when the transformer is first energized, the peak current actually could reach this level for a maximum of 0.1 seconds. So in terms of what this relay is doing, any current and time that occurs for the limited amount of time indicated on the left, it will not trip. Any current that occurs over here on the right has the potential for tripping this relay. So the way this is currently set is this potentially relay could trip as we energize the transformer. Again, as with the breakers, the relay data is set up as we characterize or set up the relay on the one line. We've indicated the manufacturer and the functions and the device that's going to be controlled. And as we go to settings, we see that we have the ability to control the upper settings and the lower settings. And here we would want to actually pick a larger range and a higher instantaneous setting. And as we do this, we've actually moved the trip too far to the right. So we want it to basically survive the inrush and yet still be able to pick up a fault current that occurs in this area of time and current. Again, we're going to be covering all this more in detail, but the advantage is, as we're making adjustments here, these can be done visually by just clicking and dragging and see what the resulting time current settings are, or make those adjustments in the temporary dialog box. One other thing, so let me close this and see what other elements I had. Let's see if this will show me what I want. So now here I'm plotting some breakers with some weird settings. You can see my thermal damage curve currently, at least this breaker, which is my BL6, the one down right upstream of the motor, has the ability to survive, at least not trip erratically on a normal start, but it doesn't seem to be effective in protecting fully the thermal damage potential for the motor start. What I want to do here is fault the bus, show my incident energy, and this is not the best example. Okay, one more thing I wanted to show while we're talking about capabilities is, and this is a curve that actually you can, if you have the smart PDC or actually the PowerProtector module installed, this file is in the samples file of the one-line folder under the EasyPower 9.7 installation. And so you can open it up and practice on this particular system. What I want to do is go in and start to coordinate this particular chain, and we'll get into more detail later. What I'm trying to show here as I go into coordination and plot this particular set of elements, there's a motor, a fuse switch, a fuse breaker, transformer, and another fuse breaker. As we plot them, I mentioned earlier that in the one-line diagram we can fault the bus and show the incident energy. So here the incident energy is very high, and it more than likely is controlled by the settings of BL2F, because obviously the lower setting on the motor, which is the isolating the motor, doesn't have anything to do with incident energy on the bus above it. So if I look on my TCC, I can see that I have several fuses displayed, and the trip settings, BL2FA, is this purple cross-hatched, and these are the dial settings for that particular breaker. As I make adjustments here, watch what happens to the incident energy calculations in the one-line diagram. So as I make these changes, you can see that this actually either improves or exacerbates the incident energy, and based upon what I'm looking for as far as coordination, I can also see what the impact is on my incident energy mitigation. Okay, that I think gets me to all the discussions about so we've looked at what the transformer curves look like, the breakers curves for molded case, low voltage power circuit breakers, relays and motors. We've looked at trip units for solid state and non-solid state. The fact that the adjustments can be made either in the temporary data dialog box. If I wanted to set, again, change the settings for BLFA, 2FA, I can make them here in the box, or I can do them, I can click and drag and change the settings in the TCC curve itself. In molded case, in the case of molded case circuit breakers, not so much because they're not adjustable. Okay, that's the basic capabilities of the TCC, what it takes to plot a TCC curve, how we're controlling the data. Now again, the reason that I emphasize starting simple is that what we've just gone through were the details required that should be entered during creating the one-line diagram. And most of the time when we receive a file and someone says, okay, I'm trying to do my first arc flash study and all I get is no protective device installed, it's because they haven't fleshed out the details of each of the breakers in line with that particular load, and most importantly, they haven't specified specifically what the trip settings are for overcurrent phase voltage or phase current. And so we'll get into more of that, the principles of coordination, starting next week. Okay, so I'm having fun. Let's see if I'm answering anybody's questions. The question is inrush primary current? The answer is yes. And that was probably misleading on my part, because what we need to be actually, and the reason for showing it was actually just the function of the relay that was being used. But the answer is yes. So the protective device will be on the primary side, and that's where we really need to be making adjustments. So I apologize for that faux pas. What I was trying to show is just the function of the relay and how it applies to different points on the TCC curve. Okay. Does newer banner have icon functions that are not in the older style ribbon format? Yes, the answer is yes. And as I say that, I don't know how old we're talking about as far as style, but as we go to coordination, you'll see that we have under fault the bus the ability to do remote voltage sensing and then faulting specifically the end of a line for any particular breaker that I pick up. And some of these capabilities have just been introduced in the short circuit in the last year or so in the short circuit feature list. So I would think yes. Okay, what type of fault used for coordinating study is a half cycle fault? Okay, so this, the question is, what type of fault should we use for a coordination study, half cycle, 5 cycle, or 30 cycle? It depends upon the other elements in the system and what your protection scheme is. The question actually goes more to calculating incident energy. So there's a multiple layer of things that we're talking about. Coordination has multiple purposes. 1, protect elements in the system. 2, isolate the function. And then 3, give us some level of mitigation of incident energy. So in terms of fault protection, you may have, based upon how large the motor is, for instance, if we have a very small motor, it may completely be offline within 10 cycles or 5 cycles. Whereas if we have a very large motor that has a lot of inertia in it, it could actually be considerably damaging or susceptible to a very long fault, in which case your protection scheme would change. When we're talking just about short circuit calculation, that's controlled, and in terms of what type of fault we're using to calculate the incident energy, that's all part of the arc flash hazard control in short circuit. And that control is essentially, in this particular control setting, usually momentary is the worst case, and so that'll give you the longest spike, the highest spike. But in terms of certain kind of faults, based upon where they are in the system and how much impedance there is and what the trip settings of the breaker, the protective devices are. Interrupting in 30 cycle may be part of the equation. What we recommend and suggest that a more accurate scheme is to use integrated for faults that have the potential to extend beyond half cycle, 5 cycle, or 30. This particular setting has the ability to actually incorporate the energy produced by each phase of each stage of current level at 5 cycles, 30 cycles, and half cycle. So the point is, the worst case current is going to be the momentary results, but it may not last as long as the fault actually potentially lasts. So by using the integrated setting, the tool understands that a long-term fault will have a decreasing amount of current, and that gives you a more accurate result as far as your incident energy calculation. That was a little long-winded, but I hope it answered the question. Can you explain the two curves of the transformer? Lots of time, fuse clips, lower left curve. Is that okay? We'll get into more details on the transformer curves. Basically, as we plot the transformer curve, we can see each of these are controlled by these particular checkboxes. And we'll get into more specific detail next week on what that means and how that relates to a particular circuit. But the intent is to be able to show you both a worst case scenario and potential derating aspects of the operation of the TCC, of the transformer, because this applies actually in more applications than just the fault. And these are areas that, and for purposes of setting up fuses and protective devices, you want to know where the time excursion is for a particular event. So yes, we'll talk about, now, this brings up another point. So this is a 30-minute session, and meant to be abbreviated and basically bite-sized. We have online under the EasyPower, this actually gets me to my last slide, to the EasyPower website, a large number of pre-recorded tutorials. There's at least 3 on protective device coordination and energy mitigation in Arc Flash. So I encourage, and these are all hour-long sessions, I encourage you to go to the site and look up the pre-recorded webinars and be able to get in more depth on all of these subjects. But we will try to cover more next week. When are the presentations going to be available? We try to post these refreshers about a week after they're presented, and they rotate through as we rebroadcast updated versions of it. So you're welcome to go to the website and get the additional information there. Okay, that's it for now. What else? We have, I think, right now 3 regional training announcements on the website, including Toronto, Portland, and it's, as I recall, I think it's Kansas City later this year. For those of you that are in a first-time mode, if you have the need to have someone double-check your work, you're more than welcome to send a file, and we can just give it a once overview as far as if you have any gross errors. But if you want to have an engineer review your work, we can actually quote on what it would take to just do a QA check or an in-depth analysis verifying that you use the proper steps for the calculations that were made, and these we quote on an hourly rate. Appreciate your attention and attending this session, and we look forward to talking to you again next week. Have a good day.